Hey folks, this is a required video in general, but if you don't have time to watch everything for Thursday, feel free to skip this one and watch it over the weekend. It's one of the finer points of the ideal gas law. But this video we're going to be focusing on the idea of standard molar volume, so kind of piggybacking off of Avogadro's law. The amounts of a gas and the volume that it takes up being proportional. So the volume of a gas depends on pressure, moles, and temperature. If we want to know the volume of 1 mole of gas, standard conditions are 1 atmosphere and 0 degrees Celsius. So actually, for any gas using the ideal gas law, this will hold. I've got a video showing where we come up with this number, 22.4 liters. So starting with PV equals nRT, at standard temperature and pressure, standard pressure is 1 atmosphere, times volume, which is what we're solving for. We're solving for the volume of 1 mole of any gas. R is a constant. Easy peasy. And then we put in temperature in Kelvin. So we divide both sides by 1 atmosphere. We get 22.4 liters. I think I took a second to put it in my calculator just to double check that I had the right value. Here's all my extra digits. But usually we just say 22.4 liters. And that's the volume for 1 mole of gas at STP, which is standard temperature and pressure. So if we know that we're at STP, or if we know that we're at a constant temperature and pressure, we're able to use volumes in place of moles for stoichiometry, because what we're saying is that they're directly proportional. The other consequence of the molar volume is that it is true for any gas. So here we have a helium sample. Let's say it's a mole of helium. It weighs 4 grams and it takes up 22.4 liters. A mole of ammonia weighs 15 grams, but because it's a gas, it still only takes up 22.4 liters. So all of these balloons have the same volume, even though they weigh different amounts based on molar mass. Alright, so let's go on to a couple examples using volumes in place of stoichiometry. So if we have 25 liters of hydrogen react with excess nitrogen, how much ammonia would be produced? And we're asked in volume, not in moles, or mass, or density, or anything, but volume. So we've worked this out by hand. No, I haven't. That's the next one. But so instead of moles of hydrogen, we're starting with 25 liters of hydrogen. And so we've got 25 liters of hydrogen. We want ammonia, so we go wanted over given. So we use the mole fractions just like we would for moles, but instead we're saying it's proportional to the volume as well. So this is the stoichiometric ratio that comes from the reaction coefficients. So when we multiply 25 times 2 over 3, we get 17 liters of ammonia that are produced. There we go. And we're able to do this very simply because we're told we have excess nitrogen. I don't have anything else to say about this slide, so hopefully you've paused it and written it down. So the reason that we're able to do this with volumes is because volume and moles are directly proportional for gases. And so what we're assuming in this example is that we have a constant temperature and a constant pressure. Alright, this is the one I did by hand. So, same reaction, but now different starting conditions. So if I have 125 liters of hydrogen react with 50 liters of nitrogen, what volume of ammonia can be expected? So, what we've got is, I've written that chemical equation up there, and the amounts of each reaction. When you're given the amount of 2 reactants, what does it mean you have to do? Find the limiting reactant. So basically we have to do 2 setups, one with nitrogen, one with hydrogen, and see which one will give us the lowest amount of ammonia produced. So we've got 2 to 1. 2 ammonia, or 2 liters of ammonia I should say, are produced for every 1 liter of nitrogen that reacts. And that cancels to give us liters of ammonia produced, and we find that it's 100 liters. I've included that decimal for 3 significant digits. The stoichiometric ratio between ammonia and hydrogen is 2 to 3. Wanted over given. See how my liters of hydrogen cancel with liters of hydrogen. And then my units in my answer are liters of ammonia. 125 times 2 divided by 3 is 83.3. So that's my smaller value. So that is the amount produced. Hydrogen is my limiting reactant. Alright, so now some practice for you guys. Grab out your pencil and paper and pause the video and go to work. Stalling, so you have time to pause it, but we're going to move forward. Oh yes, one thing that will be helpful if you're stuck. Balance this chemical equation in order to solve. Alright, so the answer is 25 liters of sulfur trioxide are produced. So this is a limiting reactant problem. We have to set up both with sulfur dioxide and oxygen. Use those mole ratios. I've balanced the equation now. And then we get 2 different answers. We're limited by the amount of sulfur dioxide we started with, and so we can only make 25 liters of sulfur trioxide. So there's just a preview of using the ideal gas law in reactions. We still think about stoichiometry, but we can use liters instead of moles when everything else is constant. Later on in the chapter we'll talk about how to use pressure instead of moles, but that has to be a constant volume and a constant temperature, as opposed to these cases where we have constant pressure. So, alrighty. So if you're watching everything in order, go on to 9.3a at this point. Otherwise, you might want to pick up with 9.3b if you already watched 9.3a for Thursday. Yeah, I don't think I have announcements. I always feel like I should have some good closer for these, but I don't at this moment. You know, you do you. Find the next thing that you were going to do, and let me know if you have questions, obviously. Shoot me an email, whatnot.